All right. So now we want to. So we have a Markov chain. When a Markov chain is defined by initial values that are evolving through matrix multiplication, where that matrix is a Markov matrix. So what is a steady state vector for a Markov matrix? I mean, I'm going to define stuff for regular Markov, but that definition can be is still true for Markov matrix. So first definition here, so if you have a regular Markov matrix, so the vector Q is called a steady state vector. So if all the entries are positive of that vector, if you sum the entries and you get one, which is like the same kind of Markov definition, and then if it satisfies the equation that if you try to transform Q by matrix multiplication, you're going to get the same thing. So it's going to be the same as MQ is equal to Q. So matrix multiplication does not change this vector. So steady state, so that steadiness, it's like cannot be transformed. And now the goal is how do we find that Q? So how do you find the steady state vector? So here, if you look at the equation MQ is equal to Q, you can bring Q on the left side. So you can bring Q on the left side and you get MQ minus Q is equal to 0. Remember 0 here would be the 0 vector. And then you can see this Q in common, so you can factor Q out. So you're factoring Q out, but be careful when you're factoring Q out of MQ, of course you're going to get M, but when you're factoring Q out of Q, you're leaving 1 behind, but 1 for matrices is equivalent to the identity matrix. So what we get here is an equation, a matrix equation, where the unknown that we're looking for, let me just use that equation here, where the unknown that we're looking for is X. So this is like the matrix form of a system of linear equation where the coefficient matrix is not M, but M minus the identity, and the augmented part is just a bunch of zeros. So this is an homogeneous system. And we know that homogeneous system, there's always at least one solution, the trivial solution, but if we only have that solution in, the sum of the entries of the trivial solution is 0, so it cannot be the steady state vector. So that homogeneous system that we get, needs to be such that it has infinitely many solutions. So does it have infinitely many solutions? And the answer is, if you look at the next theorem, so we're not going to go over proofs here, but the next theorem, if you have a Markov matrix, so this is true for any Markov matrix, not just regular stuff, the system of linear equation, M minus IN, so that's for the coefficient matrix, times X is equal to 0. That matrix here, that system, so here if you want, you can write the augmented matrix as M minus IN augmented by a bunch of zeros. This system has infinitely many solutions, and then if M is regular, then this is where it shines for us. Then there's only one steady state vector. So here, even if I say, hey, you just said there's infinitely many solutions, but in that set of infinite many solutions, if M is regular, there's only one that is going to be the steady state vector. And you need to pick that one out of the set of infinite solutions. And we'll do that with our example in a moment. So again here, so now the steps to find the steady state vector of a regular matrix M, Markov matrix. So first, you find the general solution of the system M minus IN X augmented by 0. And then the steady state vector is the unique solution among this infinitely amount of solution that is such that when you sum the entries, you get 1. So it's just one extra computation where you need to find that unique solution using that condition. Well, you know that the entries are summing up to 1. This will create an equation, and then you just solve it. Again, we'll do an example so that you can see. And of course, the beautiful part here with this steady state vector, and this is summarized in the next theorem, is that if you have a regular matrix and x0 is the initial condition of a Markov chain, suppose W is the sum of all entries of the initial condition, just like in our government versus people, the total amount of money was 6, so this would be the W in that example. Then as you let time go, so as k gets larger, so of course we use a notation k goes to infinity, xk, the states, eventually gets closer to the steady state vector q, but multiply by w. So xk approaches wq. So q is like the distribution of proportion. So if you know the total mass, that I call it w, then just by rescaling the steady state vector given by the initial condition, then you get what's going to happen in the future. So now there's basically two ways to look at how a Markov chain evolves. Either you just let it evolve, like you compute x1, x2, x3, x4, etc., and you hope that just by looking at your vectors, you can see a numerical pattern like we did in our example. Okay, we saw that the numbers were getting closer to 2 and 4. Or you compute the steady state vector, you sum up the entries of of x0 to get that w, and then you just multiply w by q, and you get it right away. So this is very powerful because sometimes a Markov chain will take a lot of iteration before you can see a pattern, a stability pattern to emerge. Meanwhile, computing q, the steady state vector of a regular Markov matrix, is a process that is always going to take the same amount of time. As long as you solve the system and you get q out, then you multiply by w and you get the future. So again, here as a remark, as a remark or a bunch of remarks, so practically speaking, the long-term behavior of a Markov chain that is regular is completely determined by the steady state vector. Using the fact that M is regular is actually a strong condition in the sense that it works, of course, for all regular matrices, but also works for other Markov matrices, but not all. Okay, but for us, all matrices are going to be regular, so for us, it's going to work perfectly. So let's just finish this set of, like theory, and let's just summarize this theory or review this theory through our example here. So here's our example again. So let's compute the steady state vector of the regular Markov matrix in the previous example involving the corrupt government. And then let's use the stability theorem to describe again, we already know, but the long-term distribution of the money between the people and the government. So solution, first we need to solve the system where the augmented matrix is given by M minus I2. So here M is 0.4, 0.3, 0.6, 0.7. So 0.4 minus 1, this is how I get my minus 0.6. 0.3 minus 0, I just get 0.3 again. 0.6 minus 0 gives you your 0.6, and then 0.7 minus 1 gives you minus 0.3. So as you can see here, your coefficient matrix is not M, but it's M where you subtract 1 along the diagonal only. And this is very typical, especially for 2 by 2. If you just go row 2, I'll add this up here. If you just go row 2 becomes row 2. Let me just write this correctly. Row 2 becomes row 2 plus row 1. Actually, this operation will always work. If you do row 2 plus row 1, you will create a row. The second row will always become a row of 0, which means that your system will always have a free variable. Like in this case, my pivot is on P. So of course what I did too here, I divided by 0.6, minus 0.6, minus 0.6 divided by minus 0.6, you get your 1, 0.3 divided by minus 0.6, you get minus 1/2. You can, even if I did not write all the detail, I did actually compute Gauss Jordan in my head, like I am computing this, I'm not just giving you the answer, but it's so straightforward that, okay, you say row 2 plus row 1, but by row 2, and then you divide row 1 by minus 0.6, and this is how you get your row 1. So anyway, so in this case here, G has no pivot, so G is free. So I can assign to G the free variable T, so infinite solution. And of course, as you read the first equation, so you get 1P minus 1/2 G is equal to 0. If you solve for P, you get P is 1/2 T. Now, if you assemble all the variables, you get P, G equal to 1/2 T, T, where t is anything. And of course, this is infinitely many solution. You want only one, but that's all right. That's all right, because the steady state vector is not any solution in that set. It is the one that is such that if you sum up the entries on the column, you get one. So we want t such that the first entry plus the second entry is equal to 1. And if you do that, you get 3/2 t is equal to 1, thus t is equal to 2/3. It's never too difficult to find that t value. And now if you plug back that t value inside Q, you get that, inside your general solution, you get that your Q, your steady state vector, is 1/3 times 2/3, which is 1/3, and then 1/2. And then if you replace t by 2/3, you get 2/3. So you get this again, but now it's a computation. And then if you want to use this stability theorem, so our initial value x0 is 5, 1. So if you sum up the entries, 5 plus 1, so 5 plus 1 gives you your 6, so that's your W value. So the stability theorem says that your states, xk, are going to get closer to W times Q, the steady state vector. So if you multiply by 6 throughout, you get to 4 again. So thus, eventually, the people will have 2 billions, and the corrupted liberal government will have 4 billions. So of course you could argue here that this is kind of longer than what we did just by matrix multiplication, and it's good to do both, to fill both. Like really a Markov chain evolution using brute force is matrix multiplication. But if you want to get to the future right away, this is solving a system of linear equation. It's never too tough to solve. You just have to be careful. Of course, you're going to deal with decimal values because you're talking about entries that are positive summing up to 1. But if you're careful, these examples are very, very nice. So you can get your future, your 2, 4, either by letting the system go forever or for a long time and trying to see the pattern, or you find your Q, you sum up the entries of x0 to get your W, and W times Q gives you your future. And again here, this Markov chain stabilized very quickly, like within 5 steps we could see, or 4 or 5 steps you could see where it was going, but sometimes it takes many iterations before you get there. So even if this, suppose this example, you would have seen this pattern after 27 steps, which would have been like hell to compute. When you are computing Q, the number of steps, like this solution that I have right here, the length of that solution is always going to be the same length. So it's delicious. Okay, so finding Q, sum up x0, W times Q. Thank you, Markov chains, where M is a regular Markov matrix. The future is in the end of the steady state vector. All right, that's it for that example. Bye-bye.